Good afternoon. Okay, so today we're going to finish up on the first part of operator overloading. So we started with a plus equals function and an operator plus. We showed that there are two very different ways of operator plus equals. Even though operator plus equals and operator plus, in a sense, perform the same operation, what we saw was that how you structure the code, how you define the input-output structure of those functions matters tremendously. Okay? And so we're going to continue with that idea today. Yeah. Question. Yeah.
I'm not sure if you went over this, but for the prefix and postfix, is there a difference when it comes to loop increments? Like, for the for, and then at the end you have the I plus plus.
Very good question. Okay, so this is actually an interview question, what the student is asking. The student is asking, okay, this prefix and postfix plus plus showed here. If you're doing a loop using a fraction, does it really matter which one you'd use, right? Should you have a preference? Okay, now, this is a very good question. The answer is yes, but really no, but really yes. Okay, so let me explain. Okay, so let's recall what is the main difference between the prefix and the postfix plus plus. Now, what I don't mean is, well, they both add 1, but one returns this previous value, one returns the value after the increment. What I mean is, structurally, input-output wise, what is the difference between these two functions? They both accept, really, that unused int parameter. Just discard that for a second. Forget about that. But what is the difference between a fraction reference return value and a fraction return value? What is the difference?
One returns like the actual object that it was called on. The other just returns like a copy of it.
Yeah, so it's the same idea when you're doing passing in a variable by reference or by value. When you return by value, you're making a duplicate copy of an object initialized with a certain value. When you return by reference, you're not actually making a copy of a certain value and creating a new object. You're merely saying, all right, well, I've maybe modified an already existing fraction object, and all I'm doing is returning a reference or an alias to the actual object itself. So no copy is being made. This is what's important to understand now. When somebody asks you, would you prefer to do, all things being equal, let's say you just have the line a plus plus or plus plus a, semicolon, period. That's it. Should you do the postfix or the prefix? Prefix. Why? Yeah, because if you do the prefix, let's take a look at the prefix. Let's look at our implementation for prefix. Okay? Do we make any copies anywhere? No. We just modify already existing values. However, in the postfix, what is the first thing we do? We make a copy. We make a copy, we increment the object itself, and then we return the copy. Well, what if we didn't need the copy? The reason we return the copy is because we want to return the pre-incremented value. But if we never use that value, right? If our purpose in calling the plus plus operator is merely to add 1 to the object and that's it, then there's no reason to have an extra copy floating around. So technically, you always want to call the prefix. If you have a choice between the two, all things being equal, it won't matter if you call prefix or postfix. You just want to increment the object. Always, always, always call the prefix. Okay. Now, before you go off and in all of your for loops write, oh my god, all my for loops are written int or size t, I equals 0, I less than n, I plus plus. I need to convert all of those to plus plus i's. Maybe, well, you could. You could. Okay? So again, let me write that out in code just so I'm very explicit about what I'm talking about is you might be tempted to say, you know, I've already posted this code online so I can delete at will. Well, let me just throw it into a lecture 3 function. Okay, now I can delete everything in main. So the, oh, I already did. Okay, so you might say to yourself, for size t, I equals 0, I less than n, I plus plus, and maybe we'll start with like a vector of ints, v of size, say 100, initialized to the value 4, something like that, and we want to see out v of I. Okay, and of course, let's just write size tn equals v dot size. We'll do the inefficient version of the loop just to show it. Okay, so you might say to yourself, okay, well, I'm a little bit better than I was previously. I know how to use size. I know size t, and I know how to use it. Okay, great. And then someone might look at your code and say, well, wait a minute, you don't use n outside of that loop, so let's throw that inside in a very slick way here. So we do comma n equals v dot size. And we don't need this variable. Then I and n only exist inside the loop. Okay, that's good. And of course, then you might say, aha, well, I learned that plus plus I is more efficient. Well, it's certainly going to be more efficient for objects. But a size t, an int, these are just variables of the fundamental type. So how the compiler interprets an I++ is probably going to be slightly different than whether I is an int or an object. The real answer is you don't know unless you actually look at what is the machine set of instructions generated by it. Okay? Now, my understanding is that putting I++ versus ++I, as long as it's an int or a size t or a fundamental type, generates the exact same code. Okay? As long as it's a fundamental type. My understanding is, I haven't verified this, but I've been told this and I believe it, it will generate the exact same code, meaning there is no difference. But if I change size t, can I make size t a fraction? Can I do that? Wait. Okay. Watch this. Watch this. Forget about this vector for a second. Fraction, I equals, well, let's initialize it. Say 1/2. And let's say n is 10. And let's, rather than calling cout, let's call I.print. There's one thing I haven't defined yet. I haven't defined the less than operator yet. Okay, this in principle will work if I define the right operator. You can write this code. Now, assuming I've defined a less than operator, now there may actually be a difference between that ++I and I++. There may be a difference. The compiler might be smart enough to know that it's not utilizing the return value and optimize it away. But there's no guarantee. So in general, yes, ++I will be at least as fast, if not faster than I++. However, in for loops where you're using size t or ints, it's probably not going to matter. Okay? So, but if you ever get asked that in an interview and they're like, well, if you have a choice between postfix and prefix, what are you going to choose? Well, I would go with the prefix, of course. Okay, so that's the reason why. Okay, the follow-up question is probably, well, why is that? Because that's what my instructor said. No, it's because you don't, right? The postfix makes a copy. In principle, it always makes a copy. The prefix does not, or it's not supposed to, if you implement it according to the style guidelines. Fantastic question. Okay, who wants to make this for loop work with a fraction? Would you like to see that? That's kind of cool. Cool concept, right? You can do a for loop using a fraction object. Yeah, I think so too. I think that's cool too. All right, so what do we need to do? Well, we need to define a less than operator. Let's see if my internet is working. No, my internet's not working. Okay, on that style guideline, it says to, and I believe, yeah, okay. You make a function, you define it, you declare it inside the class. It's called operator less than. It returns a bool. Okay. Now, what would be the parameters for an operator less than related to the fraction class? Yeah, so do we need to make a copy? If we're comparing two fractions, are we going to need to make copies of them? No, we just want to access the values, right? So if we're only going to access values, this const fraction reference can really help us track down any bugs that might occur later on. So we do const fraction reference, say left-hand side, const fraction reference right-hand side. Okay, now if we go to actually try and implement this, oh, what doesn't it like? Oh, I haven't defined it. It's picking up on the fact that I'm trying to call it down here on line 80, but I haven't defined it yet. So let's define it. Okay, here we go. Bool. Now, this is a non-member function, but I define it inside the class for a reason. Let me show you why. How would you actually define this function? What would you do? How do you determine this? If A over B is less than C over D. Yeah?
Well, I don't know if this is like a efficient approach, but you could do like convert A to like a float or like a double divide over B and then compare like double values of what they are in like actuality.
That's one example, which is very simply convert the fractions each one to a separate double, and then use the built-in double less than. See, now you're thinking. What you're thinking is, okay, I don't want to actually write any code myself. I want to use previously written code. That is the mindset you should always have. Okay? Now, what is the one possible issue with converting it to double?
Some weird size issues or like overflow or something like that.
Overflow, underflow, etc. Okay, there's a numerical accuracy that might be lost when converting from ints, the int type, to a floating point type. But otherwise, in principle, that's a fantastic idea. The cases for which the floating point will be an issue are probably not, very big deal. And if they are a big deal, then we can think a little bit harder. Okay, but as a first round, that's a good one. Yeah, in the back.
So if A times D is less than B times C.
Okay, so then you just do the cross multiply and you just make sure that the relation still holds. Now, do you have to know what happens if the denominator is negative? Then it switches. So you have to know what about the denominators? That they're positive in order to just do the cross multiply. So we can enforce that. We can make sure that no matter what operation happens, we can look at the newly formed fraction object, and then if there's a negative sign on both of them, just get rid of them both. And if one is negative, make sure it's the numerator. But we would have to have that assumption. Okay? Is there another approach? Yeah.
If you make B equal to D and then just use the built-in comparison for A and C.
Okay, so you're saying, put them under a common denominator. In other words, multiply A by, what would that be? D over, let's see. Multiply A by D is what you said, right? and multiply, wait, no, is that what did you say? Sorry, say it again.
So like a over b would be multiplied by d over d, and c over d would be multiplied by b over b. In the common denominator.
Yeah, okay, so put them under a common denominator. It's all basically the same idea. Okay? So, oh yeah.
So it's like a over b minus c over d and compare with 0.
A over b minus c over... Oh, okay, yeah, subtract the 2. And see if it's less than 0. Okay? Now, the trick with all of this is, how do you determine if the fraction is negative?
If you use subtraction, it will not matter if it's completely negative.
Right, if you use subtraction, if you want to add 1, right, so these things don't matter. But for example, if I store the fraction negative 1 divided by negative 2, is that a positive or negative number? It's a positive number, okay? So there's maybe some pre-processing I might want to do for my algorithm, okay? So the question becomes, what is the pre-processing step that I should impose on my fraction to make sure that all of my operations are consistent, okay? So let's do the quickest one first. Let's just do the comparison by doubles, just to move on to the equals. The equal operator is what you need for the homework. Okay, so I want to give you at least the bare minimum to do that one, and then we'll see if we have time to do the full reduction. Okay, so first approach, convert to doubles. Return. Now, left-hand side dot numerator divided by, okay, let's make double left-hand side. Well, no, left equals LHS.numerator divided by left-hand side dot denominator. Okay. Now, why doesn't it like that? What's that? Well, no, this is not going to be a member function. So this is a non-member function. So what's one thing wrong with this? There's actually a couple things wrong with this. What's one thing that's wrong with this? I'm trying to access a private variable. Now, I'm demanding, and if you look at your homework for homework 2, I am demanding that your operator equals is a non-member function. Similarly with less than, when we do the, I think homework 3 has you overload the less than. So there is a trick. Do you know how to give a function permission to access private variables? Yeah, make it a friend. So some of you heard this before, maybe some of you haven't. Which is, okay, non-member functions cannot by default access private member variables unless the class itself declares what about this operator less than? Friend. Okay? You call this function a friend. Now all of a sudden, the only error is that it must return a value. Let's just have it return true for now. Now that works. Now, or it compiles. Now, what's the second thing wrong with what I wrote inside the bracket, inside the code? Yeah. Say that one more time. Mm-hmm. Okay, yes, okay, yes. I need to, and the term he used was pass to double. I would use the term I need to convert to double, or apply a conversion. Conversion is the more technical term in C++. So I need to apply a cast to at least one of these, right? So let's do a static cast double on just the numerator. That's fine. As long as one of them are double, the result is going to be double. Okay? I'll do the same thing for the right-hand side. Call it right, R, R. Now I return, quite simply, left less than right. Okay? Oh, it's compiled. Let's see if this actually works. I haven't done this in a while. Okay, here we go. What do you think is going to print out? What's the first thing that should print out? A 1/2, right? Then well, if I wrote double I equals 0.5, you know, I less than 10 plus I, or so, wait, what would I expect it to print out? Or, you know, I equals I plus 1, what would I expect it to print out? 0.5, then 1.5, then 2.5, etc. Let's see what we get. Oh, let me put in a end L, a return carriage. If I put in a return carriage, then I need brackets. C out, end L. I probably need an ending one too. Cool. Okay, so by simply doing some operator overloading, now instead of just being able to work with for loops with int, you can do for loops with fractions. It's kind of cool, huh? All right. So that's why we do the operator overloading, because we want to extend this already very intuitive looking kind of, okay, it doesn't look too intuitive anymore, but you know, this idea of starting with a number, not just an int, not just a double, but a number, for example, a fraction, incrementing it by 1, printing out the value each step of the way. Okay? So that's what the operator overloading allows us to do, and it allows us to do this and write the code, instead of writing I dot operator less than, we just write I less than n, and we have the operator defined. Okay? Now, how do we check if, okay, now here's a hint. Operator equals equals is going to be almost the same. Logical structure, input-output structure, exactly the same. But now let's think a little more critically about how would you test if two fractions are equal. Okay, we don't want the friend keyword outside of the class. We just want bool like that. Okay. Will this trick of converting to double still work? Most of the time. But if you convert to double, do doubles give you really nice levels of accuracy? Yeah, there's always a little bit of uncertainty. If I try to do something like 1/3 and I do a calculation that should also equal 1/3, chances are the strict 1/3 is not going to equal my calculation exactly. So we get some problems here with numerical issues. Very subtle though. Yeah. Yeah, this one, okay, now the key observation is, okay, now regardless of whether the numerator or denominator is positive or negative, whenever you're dealing with equalities, you multiply, divide both sides. As long as you're not dividing by 0, you do whatever you want, the equality still stands, as long as you do it on both sides of the equal sign, right? So a over b equals c over d, well, this is true if, say, a times d equals b times c, right? What if I told, okay, so let's just do that one. Okay, so return, and I can do it all in one line of code too. Watch this. LHS dot numerator times right hand side dot denominator equals, let's see, left hand side dot denominator times right hand side dot numerator. Okay, this is the sort of good enough way to do it. Okay? What's the only thing that might go seriously wrong here? What if I have really large numerators and denominators, right? If I multiply two really large numbers together, I get what kind of a number? An even larger number, right? And if I go outside the bounds of what my variables can handle, then I might, what happens if you do a calculation that produces overflow?
Goes back.
Okay. It loops around only if it's an unsigned type. Okay, so if you take the largest unsigned int value, like 2 to the 32nd minus 1, for example, and you add 1 to it, it loops around back to 0. But for an int type, for a signed type, you take the largest int value and you add 1 to it, it's undefined. Okay? So overflow is the only thing that could be an issue here. Okay? What is an assumption we could possibly make that would make testing for whether or not two fractions are equal much nicer? Say again? If they're small, okay, but if they're small, we can just do the multiplication as well, and it's integer arithmetic, so it's exact. As long as it's within the boundary of the possible values, integer arithmetic is exact. Floating point is not. It's pretty good, but it's not exact.
You can reduce the fractions to make it a lot easier, but we might still encounter some problems.
What problems might we encounter?
Well, if there are no lowest common factors, or greatest common factors, whatever it's called.
Okay, but let me ask you a question. How many ways can you represent a fraction in its most reduced form? 1. So if you guarantee me that all of your fraction objects before they enter this function are going to be in reduced form, then what do you just need to check? Yeah, whether or not the top and bottom equal. Okay? So as long as you pick a standard form, a reduced fraction form, and you assume that they go into this function in that form, you don't even have to worry about the arithmetic overloading. Overflowing, not overloading, overflowing. Okay? So, this is to give you an idea. There are many different ways to implement these operators. They are not all the same. Some are, in fact, better than others. Converting to double for operator less than, that's actually not that bad. Okay? It's not the best thing you could do, but the chance that you're going to cause an error in everyday use of it is probably pretty small. However, if someone told you, hey, look, I wrote a reduced fraction form function, so you can just always guarantee that fractions are in their lowest form, then you can make even more solidly written code. Okay? And that's what I'm trying to emphasize here is, okay, with operator less than, converting them to double is not very egregious. But for operator equals equals, converting these integers, this quotient, to a double type, that's not what you want to do. Because comparing two floating point values is not a good idea. Well, not comparing them exactly is not a good idea. The alternative, one alternative is, cross multiply. Use the fact that it's inequality, so it doesn't matter positive, negative. There's not really any assumption you need. And then it works. Caveat, there might be an overflow. Okay, so just to give you an idea of, for your homework, there's really only one choice here. Because you're working with a vector of ints, to compare two polynomials, you just compare their vector of coefficients, one at a time. And you just make sure that they are exactly equal to each other, because they're ints. All right, so if I can define an equal operator, well, let's see if this works on a simple example. Okay, so I just defined. We already tested the less than operator. Let's see, did that work exactly what we expected? What is 19 over 2? 9.5? Okay. And then when we get to 21 over 2, that's greater than 10. So it seems to have worked fine. Let's replace this with 10 over 2 and see what happens. Actually, let's replace it with 11 over 2. Now, does this do exactly what we would expect it to do? because it becomes exactly equal to 11 over 2, and it doesn't print out the 11 over 2 because it stops before, because 11 over 2 is not strictly less than 11 over 2. Okay? So in this case, it worked just fine. But there's no guarantee. Let's say you wrote in another fraction there, 11 over 2, some fraction that was equivalent to 11 over 2. For example, let's try and trip this thing up. Let's try and do, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? These fractions should be equivalent, right? Okay, I can't get it to trip up easily. Okay, so I should try some prime numbers or some other. Okay, so that works. Let's try to compare two fractions. Fraction A, 1, 2. Fraction B, 3, 6. C out. A equals B. Let's see what we get. Okay, here I have to put parentheses around it. Do you see what I had to do there? That's really subtle. Look at that. Without the parentheses, what it's actually doing is it's interpreting this as that first. And then what happens is this actually gets replaced by C out. And then it's trying to apply the equal operator to B, which doesn't make any sense. It's not defined. Okay? Throwing in the parentheses is actually quite important. Okay? And we get a 1. 1 means true. 1/2 is equal to 3/6. Okay? So that's that. Now, one last thing before we define the reduce function. How about the not equal to function? Okay, so for homework 2, we've defined every single function so far except for the not equals. How would you write a not equals operator function? Say it louder. In other words, the opposite of what the equals returns. Okay? Don't write any new code. Don't write anything. Well, I obviously write code, but don't think any more mathematically. Just think logically. Logically speaking, right? If two fractions are either equal to each other or not equal to each other, and that's an exclusive relationship. So if they're equal to each other, then they're not equal to. Well, then they. Okay. You know what I mean. Okay? So we're going to define. Now, we can call the operator equals anywhere we want, right? Because that's a non-member function. I called it in main here. I wrote A equals B. There's nothing private or anything about the equals. So we're going to write our operator equals a not equals. It's going to look exactly the same as the header, except we're going to write not equals. And then what are we going to do? We're going to return the opposite of left-hand side equals right-hand side. That's it. I should probably declare, I'm going to declare this above. Along with my other non-member operators. There we go. Okay, so these are my non-member arithmetic, and this is my non-member comparison. Let's create a fraction C. Give it the value 1/6. C out A not equal to C. This should also return a 1 because it's true. A is not equal to C. That is a true thing, and we get a true. If we tried to write A not equal to B, that should return false because A is in fact equal to B, and it gives us a 0. Okay? Okay, I've been postponing this reduce function this whole time. Okay, let's do it. Let's do it. All right, here we go. So Here's a good question. Structurally speaking, should the reduced function be public? In other words, when is the reduced function going to get called? Sorry, say louder. Louder? Okay, so it's going to be called with the fraction object. Wherever the fraction goes, the reduce needs to go. Okay, let's be maybe a little more specific. Yeah.
Well, it depends on what you want. If you want all your fractions to be entered in lowest form, then it's called the constructor is called.
Okay, so yeah, so the idea here is that it should always kind of be there, right? It should always make sure that your numerator and denominator are what? In the lowest terms. Okay? When you construct a fraction using, say, 10, 2, you want it to be called initially to reduce that to 5, 1. When else would you call this reduce function? Yeah, so what were you going to say?
Just like anytime you know that the values might mutate, like this person's entering values or it's like arithmetically changing or something.
Exactly. Whenever you're performing arithmetic directly on the numerator and denominator itself. What are the only functions that can access the numerator and denominators directly? Member functions, right? Nothing else. I mean, there's a couple of friend functions, but our only friend functions make fraction references const. So you can't modify the numerator and denominator in those. So the only way to modify the values of numerator and denominator is in a member function. So we can make the assumption that fractions are always going to be in reduced form because the only way to change those values is to call a member function. And so if every time you call a member function that performs arithmetic, you get to call the reduce function at the end to sort of clean it up. Okay? In that respect, you don't want anybody else to call the reduce function. Okay? So this is probably your first example of making a function private. We want member functions to be able to call this reduce function, but we don't want the programmer who's using our library to think, oh, well, I need to reduce the fraction now, and I need to reduce the fraction again now, and I need to reduce the... No. Anytime you make a guarantee that anytime the values of numerator and denominator change, the member function that changed them calls the reduce function. And that way the programmer can always assume the fraction is in lowest terms. Okay? So let's define that function. And I'm going to make it private. So void reduce. It's not going to return anything. You could have it return a bool. You could actually have it return a bool which tells you whether or not it changed or not, but that's not so important right now. If you make it, it's always a safe bet to make a function void, return a void, because then nobody expects there to be a return type parameter. You can always give it a return parameter later. Okay? And you won't break anybody's code because, well, they weren't expecting anything to be returned anyway. Okay? But if you start giving it with a, like, oh, I want it to return bool, and then you say, no, that was stupid, I want to switch it back to void, well, someone may have tried to use it and utilize that return type. So it's always safer to just start out with a void. Okay, here we go. Let's write this. So there are two things we want this to do. So this is where now commenting becomes very important. This reduces the fraction to lowest terms. What does this mean? Case 1. What if you have something like 5 over 5? What should that get reduced to? 1 over 1. Okay? That's something we'd like to have a guarantee of, right? If it's going to be like this int over this int, that's just going to be 1 over 1. Okay? What if we have something like 0 over a? What should this return, or simplify to? 0 over 1, assuming what? A is not 0. Okay. What do you do for 0 over 0? Yeah, something. Okay. Could be an error. It's certainly a valid state for the object to be in, right? Numerator is 0, denominator is 0. But then attempting to interpret that as a fraction, as a numerical value, that is nonsense. Okay? So the state itself is not nonsense. That's perfectly reasonable, 0, 0. But the interpretation is what is nonsense. Okay? What's something else? So like 2 divided by 4, what should this get reduced to? 1/2. Okay, what about something like negative 3 divided by negative 5? 3 over 5. Okay? What about 2 divided by negative 6? Yeah, let me actually make this reduced. So let me put in a 7. Okay. What should I do? Yeah, let's make a rule, as the student suggests, that the negative always goes with the numerator. Okay? The reason is because when we print out the fraction, typically, where do we put the minus sign? We put it in front anyway. Okay? So it makes sense. It also makes the less than operator easier to write. Okay? Also, the adding 1 to the fraction does not matter if the denominator is positive or negative. Several students pointed that out. I think I said it did. It doesn't. The very simple reason for why it doesn't matter. But the point is we are going to make sure that the denominator is always positive anyway. Okay? So it requires less thinking regardless. Okay. So those are essentially my rules. How the heck do I code this in? Well, what should I do? Should I try and reduce it first, or should I try and make sure the minus sign is where it should be first? What do you suggest?
For the minus sign, you can just, if it's on the, you just check to see if it's on the denominator. If it is, multiply that by the numerator.
Yeah, so let's take care of the minus sign first, in other words, okay? So this is not very difficult to conceptualize. You have basically 4 cases. You have a over b, you have minus a over b, you have a over minus b, and you have minus a over minus b, right? Okay? So let's see. If numerator positive and denominator positive, or denominator is negative, denominator, then what should you do? So this is the case a over negative b. Take the numerator, and what should you do? So this is where you can do one of 2 things. You can either times equals minus 1, or you can do equals negative numerator. Okay, now what's confusing is you can write it like this. See that? Yeah, right. So I wrote numerator equals minus. That's not a separate operator. That's 2 things. That's negative numerator and then assignment. Of course, you could also do numerator times equals minus 1. Let's just do that one. Well, let me just say not recommended. Possible confusion with minus equals. So let's do the numerator times equals negative 1 and denominator times equals negative 1. Okay? Seem reasonable? Okay, what do we do if well, what do we do if they're both negative? Same thing. So let me combine this into just 2 different cases. A less than negative b or negative a over negative b. Okay? So let's do or. And again, let me put these in parentheses. There is a precedence here that works by default, but I don't suggest you rely on your knowledge of it or your memory of it to always just add in parentheses to make it more explicit. If numerator and denominator are less than 0. Okay? There we go. We do the same thing. In all the other cases, what happens? Just leave it. Yeah, question.
You can reduce Boolean logic to this denominator less than 0.
Yes, we can. Very good. Let's see. Okay, very good observation. So, okay, great observation. The question is, in the interest of writing clearly readable code, the way I've written it makes it painfully obvious that this corresponds to the first case, and that corresponds to the second case. The student very, very correctly and cleverly pointed out that you can reduce this to just the case the denominator is negative. Okay? This is a good thing. This is a fantastic thing. Just make sure your commenting clearly specifies the logic you're applying. Okay? Because while this is obvious, the extra thing there requires an extra small little step of thinking. And you might confuse someone that hasn't thought this completely through. Okay? So you can just write if denominator is 0, yeah, then you just negativify everything. Okay? Okay. That covers those cases. Now, the next thing I want to do, I was hoping to get this loaded up on the computer, but there is let me just very briefly explain to you, there is a greatest common divisor algorithm, and there's two different ones on Wikipedia, and I don't know if you can see, you can't see on my phone, but let me just write it out real quick in pseudocode, and then we'll look at it from there. So in pseudocode, it looks like the following. So if you want to find the GCD of A and B, greatest common divisor, that's so that we can divide through by the greatest common divisor. You do the pseudocode is while B is not equal to 0, T equals B, B equals A mod B, and then A equals T, and then you return A. Okay, so while B is not equal to 0, so I got this from the Wikipedia page. Greatest common divisor. This will allow you to determine, so the return value is the greatest common divisor. Now, the purpose of Pick10b is not to understand the ins and outs of this algorithm. The purpose is to look at this algorithm and ask yourself the following more important question. Could each and every one of you implement this algorithm? Yeah. Forget about trying to understand it. Some really smart people have already decided it works. Okay? So just go ahead and implement it. Okay? That's really the difference between computer science, like really trying to understand how the algorithms work so you can make more algorithms, and programming. Most of the time with programming, you're not reinventing the wheel. You're not really there to create something new. You're mostly just there to say, okay, I need to solve a problem. A solution already exists in theory. I just need to be able to implement it. Okay? So that is what I think one of your TAs had, like a magic function that simplified the fraction. That's essentially the algorithm that's employed. There's actually a really slick version of it. It's recursive, and it's anyway. But that's basically what it's doing. It's calculating that common factor, and then you just divide the numerator and denominator by that factor, and then you can guarantee your fraction is always in reduced form. Okay, so on Monday we will continue with a little bit more of operator overloading, and we'll get on the remaining operations that you'll need to overload for homework 3.